crossover seminars where someone from the Pheno group gets to talk to our group. And today we have Toby Opferkuch. He's going to tell us about gravitational waves and supercooled universe.
Thanks, Sean. Of course, great to be chatting to such a diverse audience. And of course, when you chat to a diverse audience, you're always in a bit of a bind as to, well, what should the level of the talk be? So, unfortunately, there's going to be some bits that might go a little bit fast, in which case you really need to holler and heckle me from the back. And there's going to be other bits that might be a bit painstakingly split, especially for maybe some of the Pheno members in the audience. So today what I'm going to talk about is using gravitational waves as a laboratory research for new physics. And I know that in formal physics, at the moment, of course, black holes becoming more and more exciting prospects for testing various theoretical developments and manners of going about super high energy physics. For us, what it really does is it presents a way of exploring the very early universe. And what this means, of course, is if you're in the very early universe, then you're at very, very high temperatures, and then you're basically in business. Because these temperatures are, of course, much, much higher than anything we can ever build in a lab. So, given this sort of topic, I'm, of course, obliged to start with a brief overview of where do we stand from an experimental point of view. And so, funnily enough, back a long, long time ago in undergrad, I actually did a research internship in gravitational wave science, more from an experimental point of view. This is in Western Australia, in the middle of nowhere, in a sand plain where you had to go to these test facilities. It was about a 6-hour drive, so you go there for the week. You suffer for the week, like 5 or 6 days, and then you come back to Perth. And at the time, as a wee undergraduate, I remember thinking that, look, the signals that these guys are searching for are just so ridiculously tiny. There's no hope that they're ever going to find such gravitational wave signatures. And so as a result, I went into particle physics. And lo and behold, we've gone full circle. So in 2016, of course, Virgo announced the discovery of the observation of a binary black hole merger. So in the bottom left is, of course, the beautiful interferometer that they used. It's 2 experiments spanning North America here. And basically what they're looking for is this sort of very particular waveform that happens as 2 compact objects in spiral together. Essentially, what they managed to see is something that looks exceptionally close to the predicted waveform here. Here is the data, here is, of course, the waveform. Of course, resulting in a Nobel Prize for a number of folks who basically spent their entire careers pushing this field, even though at certain times, especially to me, it looked like a hopeless pursuit. So that was 2016. Then the developments started coming thick and fast from that point onwards. In 2017, we turned from just observing the merger of these like 20, 30, 40 solar mass binary black holes to actually seeing something quite spectacular, namely the merger of 2 neutron stars. And this is somehow a little bit different to binary black hole mergers. The reason being is when you look at the binary black hole mergers, what you get to do is you get to see the waveform for a very, very, very brief period of time. You basically see the final chirp of these guys coalescing. However, just due to the masses of neutron stars, when you see a neutron star merger, what you get to do is you get to observe it for a significant period of time, 30 seconds, as these guys are finally spiraling and coalescing. And beyond that, of course, there's a huge number of other applications, but I just want to talk about one of my own sort of applications of this style of physics. Is, well, if you get to watch this guy for a really long time, what you actually have is you have a system where you can essentially test gravity on a very unique length scale compared to other tests of gravity. And the reason being is that you essentially have 2 neutron stars acting as test masses, and you get to test Newtonian physics when they're far apart, and then GR as they get closer together. However, from a particle physics point of view, these neutron stars are also very, very bizarre objects. I'm not sure if it's common knowledge, but beyond neutrons, of course, these neutron stars also harbor a number of muons that you literally will not find anywhere else in the universe, something like 10 to the 55 muons. And all of these guys are left-handed. There's no right-handed muons in the neutron star, simply due to the weak force being in equilibrium. And as a result, you can use these neutron stars as test masses to basically test exotic long-range forces that couple with muons. So that's like one cute little application of such an observation of neutron stars in spiral. However, the show goes on to about 6 months ago. And what we had 6 months ago was something that's really quite fundamentally different to the observation of an in-spiral in an interferometer. What actually happened is we seem to have the first observation of a genuinely stochastic gravitational wave background in a medium called pulsar timing arrays. And here the idea is very different. For the interferometer, of course, we had some experiment with lasers pointed along two long baselines. Basically, a gravitational wave comes in, distorts the baseline, and through laser interferometry, we're able to measure this change of length in the arms. Now with pulsar timing, what we do is we do something really quite different. We point radio telescopes in the sky, and basically what we do is we look at the very best clocks in our immediate vicinity, which is actually the form of pulsars. And pulsars are nothing other than a rotating neutron star that's beaming particles in a certain direction that changes as they rotate. However, these things rotate with such a steady period that if we're looking for something and we see these, we're in the line of sight of one of these beams as we rotate, what we're basically going to see is we're going to see a flash of particles every time this neutron star rotates around. And these are absurdly good clocks. So much so that if we time a number of pulsars, what we can actually do is we can infer something about the gravitational waves that are passing in between us on the Earth and the different pairs of pulsars that we're measuring. Of course, this is a very difficult endeavor, and there's been a number of large collaborations across the globe that have been doing this for a good 30 years. And finally, what they're starting to see is some evidence for very, very, very low frequency gravitational waves propagating through the universe in between the pulsars and us on Earth. And so what I've shown here is what's called a violin plot, as they affectionately call them. On the y-axis is the amplitude of the gravitational waves in question. The x-axis is the frequency of these guys. And what there basically is for two different sets of data is posteriors on the range of the allowed amplitude for a given frequency. So you see something like this bin here. You see that the posterior is such that there is evidence for a non-zero amplitude in that frequency bin. What you can do is you can go then look across all the frequency domains and then look if there's some sort of best fit power law to this sort of posterior of each frequency bin. And what you find is that there is some support for some sort of signal with a power law in this frequency domain. So this is a very, very cool thing. However, I think the question here now is, well, how does this all really connect to fundamental physics? Of course, when we build these experiments, we're going to learn a huge amount about astrophysics. For instance, what you would expect from an astrophysical point of view is you would expect to learn something about supermassive black holes merging. And this is the sort of thing that is most likely to populate this very low frequency bin.
Toby?
Yeah.
How sensitive to primals are these plots, and why a power law?
Why a power law? Well, I don't know if you saw the talk from the RPM a couple of months ago, but essentially if you go and simulate, so basically what you need to do is you need to do a population study of all the supermassive black holes and over a distribution of masses. And what you can do is you can go along and do a population study and study what is this spectrum of gravitational waves you expect from supermassive black holes emerging. And of course they find it's something that really isn't a power law, but nevertheless what you're looking for power that's correlated across different frequencies. This is the sort of thing that you would expect for any sort of signal, be it new physics or astrophysics. And then a power law is just a choice of something to fit.
So, I guess that what I'm actually trying to ask is, can you claim a discovery without modeling? Is it possible to say?
So what you need to do is you can't model all of the noise when you time various pairs of pulsars. However, what you do is you look for the Helling-Downs correlations. And what this basically tells you is because gravity is a spin-2 guide, it predicts a very particular pattern if you time different pairs of pulsars with different angular separations in the sky. So if you get enough statistics and you understand your systematics, then you can extract this sort of curve. And basically, if I remember correctly, it basically is something that looks like this. So across the x-axis is the angular separation. So this would be the angular separation from small to large. If it was some sort of noise, you wouldn't expect it to have this particular pattern as you would to different angular separations. We'd rather expect something that is like flat or something else that is completely randomly distributed in these different angular separations of the pairs of pulsars that we're taking. Does that help me out? Because otherwise you would just you'd be like, okay, there's a bunch of noise in these measurements. I don't know how to extract that noise from that signal. And that's the main means by which you can say, that's gravitational waves, and that's noise. So what does this all have to do with high-energy physics? Well, the current place I find myself in, and the way I'm currently thinking about looking for new physics on the Standard Model, is really through the union of these two fields. On the left-hand side, we have, of course, the Standard Model, particle physics. On the right-hand side, we have the Standard Model of cosmology. It might be a bit of a controversial opinion, but my kind of feeling at the moment is cosmology is a good 10, 15 years behind particle physics, but it's very likely, much like particle physics, where in the future we might find that we have a very good phenomenological model of what's going on, but understanding the physics that actually determines these parameters is going to be very, very difficult. So really, my main aim here is really to throw the kitchen sink at the problem. And in that way, hopefully through some sort of symbiotic relationship, we can maybe help one another out. And the idea is of course, this is the beloved thermal history of our universe from very, very early times to today. And on here I've marked a couple of key places. What was that? Any white
I like the fact that you've got a reheating here. A lot of people leave out the reheating, so I was very happy to see.
The reheating is very important.
Yeah.
So anyway, we have some sort of inflationary period with reheating. And as soon as we reheat, we have a hot thermal universe that expands and cools. And now, really, if we know a little bit about a slice through the inflationary epoch, through CMB observations, then we know another slice through Big Bang nuclear synthesis and the fact that we had to make heavy elements. And then we know quite a lot about how things look today. So really we have these marker points or goalposts throughout the very early universe. And essentially, what we know today is quite a bit, but there's really a large number of ways of connecting the dots between the phases where we do have some sort of idea of what's actually happening. And in particular, for what I'm going to talk about today, is there is this notion of at least 3 or more phase transitions being likely in the early universe. The first is, of course, we inflated, And then we had a hot thermal universe. That's a spectacular phase transition from omega equals 1 to radiation dominating. Then we could also have, if the reheating temperature is high enough, something like the electroweak phase transition, where we go from a temperature just above to below. And depending on if there's new physics or not, the nature of that could very easily change. Down to, of course, the QCD phase transition at hundreds of MeV. So what we know is there's at least 3 transitions in a very early universe, and very many more are possible. And so why is gravitational waves a good way of going after these phase transitions? Well, there's 2, I think, important ingredients for this. And the first is, of course, the fact that the universe is very transparent to gravitational waves. As we know, at least at large scales, gravity is very weakly coupled. So with the CMB, of course, we can only look back so far before we hit the fact that the universe is a charged plasma. And any information before that is washed away by the fact that our photons are going to be, they're free in this phase where there's no charges, and then all of a sudden you hit a plasma or charged particles, and any information from earlier times is completely lost through multiple scattering. Gravitational waves, of course, don't have that problem, and as a result, we can see back further in time. So that's handle number 1. Handle number 2 is maybe a bit more related to particle physics and model building. And that's the idea, of course, that no matter what shenanigans you're busy playing, you can't get around the fact that everything couples to gravity. And so what this means is that if I'm willing to play cute games and stick my standard model in one sector, and then have some sequestered dark sector, of course it's very model dependent how these things talk to each other in terms of new fields and the standard model fields. However, what you cannot escape is that gravity will communicate between these 2 sectors. And in particular, I worked a number of years ago on this signal that I showed you in pulsar timing. One of the first questions that I asked a long time ago was actually, could you build some sort of model where you had a dark sector that underwent some sort of transition that would explain the signal? And the answer I found is no. This isn't possible through phase transitions. And so given this recent result, there's been a huge amount of work as to, well, actually maybe is there some way you can get around these constraints? Because essentially if you want a big enough gravitational wave signal, there's also constraints coming from other cosmological observations that really put this at tension. So really the point is historically in physics, what we've always encountered is the fact that we tend to learn a lot about the system if we study the phase transition in question. So for instance, of course, the main example I can think of is of course superconductivity. And really in studying the dynamics of the phase transition and the critical phenomena, this really gave key insights as to what is actually the microscopic behavior of the theory. And so it's my hope really that in studying early universe phase transitions, we might also be able to use these as a way of understanding better what is the microphysics actually involved. Of course, it's a little bit more challenging than boiling water in a pot. Our universe is, of course, much more complicated, but nevertheless, this idea of a boiling pot of water is quite useful. Because the main transitions in the early universe that actually produce gravitational waves are the ones that are first order. And what this basically refers to is just the fact that I make bubbles of a new phase that expand and collide with one another. And this is the key mechanism in a phase transition in the early universe with which one can source gravitational waves. So, of course the picture is very, very different compared to my boiling pot of water. But first what I should probably do is put things a little bit in context. Because before what I showed you this detection in pulsar timing arrays. I told you it was low frequencies. But where does this fit into the big picture? Of course, low frequencies here, and I mentioned something about supermassive black holes. How do all the pieces come together? And so the way I like to think about this is again on this same plane, amplitude against frequency. What I've plotted here are all the current observations that probe points that would live in this plane. So at high frequency, we have the laser interferometers. These probe frequencies in the hundreds of hertz. They live up here. While these probes at extremely low frequency, through pulsar timing, live down here in the 10 to the minus 8 hertz. In those times of like a year, 10 years, 20 years. And so if you're staring, looking at this plane, you're like, well, there's quite a large amount of light space. What's actually going on here? And well, the first thing you can think of is you think of, well, what are other ways of looking into this plane? And the first thing that comes to mind is what's called delta N effective. And this is just an observation during either the CMB epoch or the epoch of Big Bang nucleosynthesis, where essentially what you are learning about is you're learning about how much energy there is that's behaving like radiation. And what we're able to do is we're able to place a constraint. And funnily enough, gravitational waves that are propagating inside the horizon to an observer like us, they just look like radiation. So what this means is that there's a limit on how much energy density we can have in gravitational waves. It doesn't matter about the frequency, it's just a raw quantity. And so that gives me this line here. And so everything above that is ruled out. So then you sit there and ask, well, what's actually going to happen in the foreseeable future? And here you can see a plethora of experiments ranging from the quite crazy to the funded and going to happen. I'm not going to comment on which ones are the crazier ones, but you can make up your own mind. So of this plethora of experiments, a number of them are very exciting. Of course, the one right smack bang in the middle is LISA, which is going to be a space-based interferometer, where basically you use huge baselines in between satellites to shoot lasers and look for gravitational waves that distort those distances, so something like 10 to the 6 kilometers. So this is the reason why if you start with your ground-based interferometers, of course if you have a longer arm length, you're going to have sensitivity to lower frequencies. Then at the higher regime, what you have is you have Einstein Telescope or Cosmic Explorer, which are going to be the successors to the LIGO-Virgo program. And in addition, what I've not put here is that there's of course going to be an ongoing effort in pulsar timing, so much so that telescopes like the Square Kilometre Array and other big radio astrophysics missions are going to also slowly be able to peak further down in the far left. So what lives here? And the point here is that there's a huge number of things that can populate this plane, from just the inflationary background, which would live, unfortunately, somewhere all the way down here, given our constraints on Hubble during inflation, to things like phase transitions, which I'm going to talk about. If you non-perturbatively produce particles through rolling scalars, you could have networks of cosmic strings that Ben's very interested in, all the way to topological defects like domain walls and other fun things that could populate the early universe and lead to a signal. And to give you an idea of what actually sits here, here I've actually showed a first order phase transition in this plane. And the cute thing here about a first order phase transition is the idea is you make bubbles, they get nucleated, they expand, and they collide. And so what actually happens is that the peak of this broken power law is basically determined by what is the size of my bubbles relative to Hubble at the time. This tail here is to do with causality, while this other tail here basically encodes information about what is the environment in which my bubbles are made. And really the beautiful thing about looking for first order phase transitions is something I hinted to at the beginning, is, well, what dictates where this broken power law sits? And the mechanism which dictates that is essentially what temperature did the phase transition occur at. And as I go to higher and higher temperatures, higher energies, then what I see is this corresponds to higher frequencies. So if I have something that is sitting here, this corresponds to a temperature of 10 to the 5 TeV, which is much, much higher than any sort of direct terrestrial probe that we currently have of new physics. So that's really one of the main motivations here, is these future ground-based experiments will really be able to have a reach that is very, very high in temperature. And that's really, if I'm going to be honest, what we're going after. So now that I've given you a not so brief intro as to what's happening, I'm just going to quickly mention a little bit of my own work on supercooled phase transitions, and mention a little bit about simulations and how we're going forwards making these sort of predictions of these cosmological phase transitions more robust. Because as you may have noticed, there was a huge band over this prediction. So really, phase transitions are kind of an interesting beast in that from a particle physics theory point of view, there's a huge number of different theories that we can write down. However, from understanding the dynamics of the phase transition, what we really want to know is we want to understand what is the free energy and what is the order parameter. And so starting from any of these theories, you usually have to do quite a bit of work to get to this point. For instance, if you were studying the standard model and extensions thereof, what you want to do is you want to understand the electroweak phase transition and how this can be made first order. To do so, you need to do a bunch of thermal field theory and understand how the Higgs potential actually evolves as a function of temperature and whether you have some sort of distant continuity in the free energy. So what's kind of happening at this point is that there's a lot of theories and there's not that many different structures that the free energy can exhibit. And much like condensed matter, it kind of hints towards this idea of there maybe being some sort of organizing principle, be it through universality classes or critical phenomena. It's really a little bit of an unexplored landscape in particle physics, namely because going from here to here is so painful. And to this end, what I've mainly been studying is this idea of a supercooled phase transition. And I'm going to get back to that briefly, but what's important really is, again, like I said, you calculate this potential, which is just thermal field theory. And what you want to do is calculate this order parameter, which in this case would just be a scalar field, and the amount of vacuum energy that's liberated in the transition. So with those two things in hand, you might think, well, I'm home and host, but all this has told you is that, look, there's this much energy, and it's going to be probably liberated at a certain time. What you then need to understand is you need to understand, well, what are all the processes that actually affect, if I had take energy density, how likely is it to make gravitational waves? And to that end, what you need to do is you need to first understand how much energy is available, and secondly, what is the efficiency? And the first thing here that's very useful is our understanding of how much energy is available as a function of temperature. So this would be a decrease in temperature, increase in time. Here, this black line would be my energy density radiation, so the standard model plasma. And of course, as we expand, this radiation bar drops. And for a given model, there might be a certain amount of energy that is liberated when this model undergoes a phase transition. And so, if you choose some random time for this phase transition to occur, let's say it's this point here in time, the amount of energy liberated relative to the energy in the bath is very, very, very small. So what you would see then is, yes, you have a first order phase transition, yes, you can make gravitational waves, but there is a huge suppression between these two guys. However, if you wait longer and longer and longer and longer, what you'll see is that eventually this purple comes to dominate over the energy density of the standard model plasma. So what does this mean? Well, this means that you actually have a phenomenon which we have termed supercooling. And what this basically means is that it's just like maybe the CC today, you're now entering a phase of vacuum domination, except this vacuum domination is by some random new physics that's in a sequestered sector compared to the standard model. And what this means now is that if a phase transition in this sector completes any time after this equality point here, what this means is that it maximizes the available energy. This energy is always going to dominate over the background, and therefore you have the highest chance of producing something that's observable and that will populate this plane that I mentioned before.
Question, which is, you know, I agree that you want to get to where the two lines cross, but there's probably not much advantage to going to extreme supercooled.
There's extremely bad consequences if you go too far.
It starts to inflate for one thing, but
yeah, but it's not to inflate.
so when is your aim just to get close to where the lines cross? Or?
Yes.
Yeah.
You don't want to be too far apart, otherwise you end up stuck in eternal inflation. And your life is a bit miserable if you're interested in reproducing what we observe. So there's definitely a sweet spot. But the point is that here, of course, you're falling very fast. So if you're on this side of the curve and you want to have an observable signal, you need to be tuned very close to this equality point. Whereas if you're on this side, there's a lot less tuning that's required for you, this signal to be observable. Because all you need to do is basically make sure that you don't end up in eternal inflation, and you know you're good. So there's none of this pressure about being tuned really close to this, much like vacuum domination today. Like, why do we find ourselves in the universe that's just started under vacuum domination? If you saw a strong signal, and this was, you confirmed the model had to live here, you'd be scratching your head as to ask, well, why there? So supercooling is a way of getting a strong signal, relaxing one of the tunings, essentially. Of course, you always pay a price. It's no free lunch, but that's the general story. So this maximizes the energy. The second part of this toy equation is the efficiency. And the efficiency here is really dictated by the pattern of bubble nucleation and the expansion nucleation. And so the energy density in any given bubble is proportional to its volume. And what you find is that the vast majority of perturbative models, at least, predict a nucleation rate where once you make one bubble, you make trillions and trillions and trillions of other small bubbles at the same time. So your phase transition is basically completing by filling your volume with small spheres. Based on this idea of the energy density being proportional to the volume, this means that this collision of small bubbles is actually going to be less efficient at producing gravitational waves compared to the case over on the right-hand side, where I might make a few bubbles and they have time to expand because there's no other bubbles being nucleated nearby. They expand, and then once they collide, they're much, much bigger compared to on the left-hand side. And it's really this right-hand side where you have a much more non-trivial distribution of bubble sizes, where you actually end up maximizing the size of your aperture. And actually this is great because in supercooling you have this small period of inflation, and so this also further helps to maximize the bubble size and also increase the distribution, the width of the distribution of the sizes of said bubbles. So this is just one source that I chose to illustrate that dictates sort of the efficiency in making gravitational waves from colliding bubbles in a phase transition. So there are many other further things because, of course, you have to understand that we're making these guys on a plasma. My bubbles are going to interact with the plasma. There's dynamics as particles go through the walls of the bubbles. I mean, the list is long, and this is really just the tip of the iceberg. Nevertheless, we now have an idea of how do we make sure there's lots of energy, how do we make sure the efficiency is high, what does this mean from the theory landscape of models. And what we basically went after is we went after models that are basically quasi-scale invariant. And the reason being is that these are the models that really give you the strongest amount of supercooling. Essentially, these models are quite special due to this classical scale invariance. When you compute thermal corrections to these guys, they give you a very particular arrangement of coefficients. such that you end up with a very strong first order phase transition. And really, the question is, well, this is very non-generic. Of course, if you look at the standard model, it's so far away from being a scalar invariant theory that it's laughable. But here it's really about understanding if we have these scalar invariant theories and we perturb them, we softly break them. It's really about understanding what affects these small amounts of breaking of conformality or scalar invariance. What effect does this have on the gravitational wave predictions? And that's essentially the main thrust of this piece of work. And so what you start by doing is you start with an example. And this is the dumbest kind of model you can write down. This column winds at U1. You have a scalar, it has a U1. And basically, essentially what you have is through radiative symmetry breaking, you generate a scale. And then you also have the gauge coupling from this U1. And you can ask, well, depending on my scale, how big is the range of gauge coupling where I produce supercooling? And this guy is shown in blue. And what you see is that it's not too bad. I mean, 0.4 to 0.9 odd. It's a reasonably large window. And on top of this, it's also probed by current experiments in orange, future experiments in gray. Again, it's a very busy plot. It's cut back to these 3 experiments that I'm interested in the near future. You see that you start to probe quite a significant fraction of this region of parameter space. But what's more important is what happens when you deform the model. And so what we did is we just took this U1 theory and we started to add operators of the form here and systematically categorized how these different ways of breaking scalar invariance, how do these disturb the phase transition. And I'm not going to go through all of the different ways we went about this, but what we did find is one kind of surprising result. Because the common law is essentially that if you add these sort of explicit breakings of scale invariance, results in the literature really suggest that you destroy the gravitational wave signal really fast. However, what we found is that there are particular deformations where you deform with a cubic term that actually lead you to enhance the size of the supercooling window. And so before, in this plot, I was showing you a slice here. What you see is that with this deformation, relative to the generated scale M, what you actually see is that you now have a larger range of parameter space from this large value of like 0.8 odd all the way to essentially 0, where you can actually build a successful supercooling model. And now, of course, this is just at the level of a toy Lagrange where you add an explicit breaking. There's a bit of work that needs to go to map this back to models, but for the few people in the audience, there are some like Yukawa models from Joe Dini company that actually are secretly doing this. You just don't really realize it in the construction that they built. So that's the rough story there. And now I want to just take a step back and then just mention really what I'm doing now and what does this program look like going forwards. As I've said, there's quite a bit of detail in going from a model to a gravitational wave signal. I've spoken a little bit about some of these aspects, from calculating the phase transition to the type of bubble manipulation dynamics. But what I haven't really talked much is that once I know how my bubbles are created and how they expand, how do I actually calculate what the spectrum of gravitational waves look like? And unfortunately, this is quite a difficult procedure, as what it requires is cosmological lattice simulations. Just some sort of like classic lattice simulation where you track all the tensor modes of the strings relative to your background scalar field that's exhibiting this dynamics. And so in this first part, I really focused on how you go from A to B. The rest is now going from B to C. And the point is, again, there's lots of models, but of course, for every model you can write down, you can't go and like hit play and do a cosmological lattice simulation. This is just not possible. These guys are extremely cost intensive. Even though it's a very, very simple differential equation you're writing down instead of differential equations, running a small simulation here is about 180,000 CPU hours. And this was just for a box of 64 bubbles. So this is, of course, a very small number of bubbles. You want to go to larger boxes with more interesting distributions. Doing so is just completely infeasible if you want to simulate every single model you can write down. So what you really need is you need signal predictions for the theories that aren't very well covered, and you also need to come up with a map, mapping your particle physics model to the initial conditions of a simulation, and then using the simulation to the final results. And so this is what we are currently trying to improve.
How does the calculation cost scale with volume? Is that, you know, if you want to make the volume twice as big?
It's not so much about making the volume bigger. What you want to do is you want to go to, well, you do kind of, what you want is you want to go bigger in your volume, but you want better resolution. Because the point is that as the bubbles get bigger, the bubble wall Lorentz contracts, and so to actually properly resolve the bubble collisions, you then need an even finer lattice to resolve those bubble walls when they collide. And so I've forgotten the scaling and volume, but this is exactly why we've been using adaptive mesh, because essentially when these bubbles are nucleated, they expand. There's a lot of the volume that we simply just don't care about. Like, okay, for thin wall bubbles, the inside and outside is boring. For thick bubbles, there is some range where the scalar field inside the bubble is actually still oscillating. But you don't need as much resolution as the bubble wall. And so the idea here is, with my bubble walls, I of course want as much detail as possible, while for the interior of the bubble, I largely don't care. All the juice is going to be in the bubble collisions. And so the idea here is that we can go to bigger boxes and study bubbles that expand for longer through the introduction of refinement along the sides of the bubble walls.
Do you resolve full spheres or just contours? Right, so here you have overlapping bubbles.
Yes.
You care about that?
It's a 3D simulation to begin with.
No, of course. Now, okay, for simplicity, I have two spheres.
Yes.
If one of them is inside of the other, it doesn't make sense in...
Yeah, so the whole initial conditions are chosen so that when you nucleate bubbles, if there's a bubble that exists in the simulation volume that's too close, you actually don't nucleate it. Because the only solutions that we have at this point in time are spherically symmetric, like ON bubbles. And so if you get closer to a bubble that already exists, naively your expectation is that this deforms your probability for producing a bubble, right? It's a bit like boiling water, that you make bubbles on this boundary or on impurities. And I'm thinking of like a non-trivial scalar field configuration. This is in spirit the same thing. As you get closer to a bubble, this potentially increases your chances for producing a bubble, but you're not going to make a spherically symmetric one anymore. You're going to make something that deforms what's already there. And this is not taken into account in these simulations so far. We only make bubbles when they're far enough away from existing structures. So I mean, all in all, these things are still quite primitive and have quite a long way to go. But they're getting good enough now that we're actually able to make some predictions that don't just out and out suck. Because I mean, it's a very delicate business, because at the end of the day, you're going after things that are hidden behind astrophysical formats. And so what you're going to want to know is you're going to want to know better than just a broken power law. If you're looking for a broken power law, I can name you 100 astrophysical things that might give you a broken power law. You're going to have some sort of finesse about some sort of features or some other smoky gun you can go at in order to disentangle it from other things that might be there. So that's part one. The second part, here's how it looks so far, I guess. It's not the highest resolution simulation at the moment, but it gives you an idea about the sort of what's kind of happening in the interior of the bubbles, and when the waveforms are actually colliding with bubbles.
Maybe in these supercooled cases, you have some simplicity compared with other situations where you have to deal with a lot of the turbulence of the fluid and so on outside the bubbles, because maybe that's not so important.
Yeah, also, this is where a little bit of inflation actually might help, because it's going to lower a little bit the relative importance of the background plasma.
Yeah.
So that's actually the hope. This is why I'm going after the supercooling case first, because one, I think it's the best chance of there actually being a signal. And two, looks like there's a little handle for sucking less at predicting. Because just the number of things I've skated over is immense. This is not like this is a business that people have been working steadily on for a good 20 years, maybe a bit longer now, for like 30, 40 years now. But it's really with the observation of gravitational waves that it's become somewhat more important compared to before. So the last thing is then, okay, great, you can do the lattice simulations better, but wait, didn't you tell me there's a plethora of models? How do I know which models to test? And so the idea here now is that we build some sort of module that, as an input, takes your particle physics model. And what it does is based on the precise dynamics of your potentials or the things of your free energy. It basically does like a little mock bubble simulation. And basically sets the initial conditions that you would expect for this sort of cosmological phase transition. And what you can do is you can use this to nucleate a certain number of bubbles. And then once you have that initial condition, you can feed that then into a lattice simulation. And okay, this is not like rocket science or anything, but the nice part is that what you find is that there's a large number of particle physics models that map onto more or less an identical initial condition for the lattice simulation. So this will give you a very fast, robust way of saying, look, all of these models basically give you the same initial condition. This other space of models map to this other distribution. And this is something that is a little bit lacking for the more exotic sort of phase transitions that aren't just the electroweak phase transition. So that's the current endeavor. And then going one step further is, well, you can look at these simulation volumes and you can be like, well, you know, there's only a certain number of configurations of bubbles actually colliding. And the hope is that what we could do is take a space of like a library of all the 2, 3, 4 bubble collisions you could dream up, run simulations of them, build a library, and then using this library somehow extrapolate to the full simulation volume and approximate the gravitational wave signal, rather than always having to run a full simulation every single time you want to know the answer. Of course, this has a number of limitations, but it might be helpful as like a fast gravitational wave simulation for just giving you a rough idea about what's happening before you bother to go into all the very nitty-gritty details.
Is there understanding why so many different models give the same initial condition?
No. Well, yes. No is probably a bit quick. Basically, the reason is that most, if you build like a perturbative model, basically what happens is that usually this implies that the phase transition is very, very fast. And so what this means is that you're much more likely to get a phase transition that looks like the left-hand side, where all of the bubbles are more or less the same size. There's no time for them to expand, because you just filled the volume with small bubbles. So for the most part, this is what you would expect from all these single extensions of the standard model. All these sort of things will look like this. So phase transition will be fast, bam, done. Supercooling and other things that can give you more interesting distributions, and these transitions generically take longer. These are the sort of cases where there'll be much more non-trivial distribution, bubble sizes, and this sort of thing will be more important.
But isn't it still true that by the time you meet the third bubble, the first two ones are going to be very similar to one bigger bubble?
Yes, this is why you think you have a handle in maybe simulating 2 and 3 bubble collisions. Yeah, because the hope is that simulating even 2 bubble collisions might be enough, and that you can just if you have a simulation of two bubbles
Yeah,
colliding,
just to pair them.
you run it for a certain amount of time, and you truncate the calculation when those two bubbles hit the third one. Because obviously you've gone outside of the range of validity of that.
Yeah, no, I'm just saying, like, in practice, if I want to say that I know that I have some kind of transfer function of some sort, it takes two bubbles and give me signal. And then I would assume that it is going to look to some approximation like many pairs of bubble collisions, because the third one is going to collide with two that look similar to one bigger bubble by the time or at least around the surface of collision. Okay, cool.
That's
Amazing.
because yeah, running everything every time is just a bit outrageous. At some point you look at the energy bill and you're simulating things that are maybe tenuous to exist. Anyway, on that note, I'll end more or less here. So I think there's three main messages that I'd like everyone to trundle away home with. Is that from this plane, obviously you can see that really there's a huge amount of progress in the coming 10-20 years about ways of probing different gravitational wave amplitudes and different frequencies.
You're telling me that all of this lot will be done in 20 years?
No, this is why I showed you three. Matt, let's look at asteroid ranging, definitely. So given that a lot of these experiments are going to exist and are going to be chiefly built for looking at astrophysics, I think it's still very important that we spend a bit of time still making sure we haven't missed anything that can populate this plane from a theory point of view. In the last 10 years now, there's been quite a few new ideas or twists on old existing ideas that have been quite interesting. And I imagine there's a lot of very creative people out there, and I imagine this is going to continue. So I think this is something that's very exciting. And then once we have a rough survey of what's possible, then really going and taking the more motivated scenarios and making sure that we have concrete theory signal predictions so that we can try and disentangle these things from backgrounds. And so for me, what this looks like is really going after these supercooled phase transitions and really making sure that we're in a position where these lattice simulations are up to shape for the task at hand. Thanks for your attention, everyone.
Perhaps you could use machine learning to accelerate your simulations. Like, I'm curious to what extent would like video observations of actual like bubble activity within liquids or fluids that you could video record could be similar training or relevant training to a neural network learning to recapitulate these kinds of bubble propagations in this exact context. I mean, is there such a thing as relevant? Because the background is that there's been progress in machine learning where there's been like, in some cases, like several 100,000 times fold acceleration of simulations of physical phenomena kind of like in this setting. So if you could manufacture some training data instead of without having to run simulations, right? that's similar, then you could potentially then subsequently learn to do this kind of thing.
For sure, I think also, like you said, maybe there's also more exotic media that you can produce, like observable, like lab observable phase transitions in that might be better at mapping back to the case of the standard model plasma with scalar field, which is of course very, very different to water, but I'm not too familiar with what other physical systems exist, like maybe some sort of superfluid system, superfluid helium, or some other bizarre system might have something that is maybe more well suited. No, I haven't thought about that.
There's an interesting question. Are there people think, sorry, do that. Are there people trying to map sort of, real experimental physical system to?
There's been a little bit of an attempt to do this, but I I really feel like just the setup of how a scalar field works and how particles passing through this topological configuration of the scalar field, how this actually that reacts and affects the bubble expansion. Because essentially, the main source, if you have a plasma or gravitational waves, is actually the acoustic modes that you excite in the standard model plasma. And you know, your first thought when you hear this is like, well, engineers have been studying fluid dynamics for like an eternity, surely they get to solve a problem when this is done. But the actual mechanism by which you dissipate energy through turbulence is quite different in the standard model plasma compared to in your car, where they've really got the nail down.
Also, I would assume that all four invariance makes things very hard to simulate, right? You need something to expand just as fast as you pop the next bubble, like for any physical analogy, I would assume that relativity is like a big harder to tell.
Yeah, because these bubbles are being made and expanding at the speed of light.
Yeah.
And so, of course, the most violent cases is where they have a lot of energy and they're going real fast. Those are the ones you're after, and those are the furthest away from the physical system. That we've got observed in the lab, at least, that I know of. Wow, lots of caveats in that sentence. Yeah.
So I'm wondering if you're aiming, if you think that the simulations could, is the aim to get the slope of the power law at high frequency, or is it to get the detailed structure of the peak?
So the one I want to go after also is the structure of the peak. I want to know the peak because that's the thing you're most likely to see.
Right.
And it's the place where I think you have the most available information. Because if you just say your amplitude is huge, right, and you just see the tail far out, I think at this point it's going to be very difficult to disentangle that from other sources. So at that point I'm like, well, it's questionable if you should burn so many matches going on. Whereas if you see the peak, you start to see it falling in some sort of roughly parallel behavior, I think it then becomes a bit harder to model those other sources.
I see. So, I mean, you could imagine a situation where the peak, unfortunately, is a frequency where the experiments are.
Yeah, right here. It's like right here.
You could imagine that actually the power law cuts that you do see, not the power law. But you're saying that using astrophysical backgrounds could give you a power law of many decades. I was imagining that might be rare.
In this frequency regime here, where you have these unresolvable compact binary backgrounds that have some specific shape, they definitely be backgrounds over a decade and a half, 2 decades if you're really unlucky. Low frequencies, supermassive black holes. High frequencies, though, you're more or less in business. So the further you go out this way, the less hard work you have to do against astrophysical backgrounds. This is why the whole super high frequency gravitational wave thing is kind of cute, because there is no astrophysics, except for ineffective. But yeah, that's a story for another day. Good. Any other questions? I mean, it would be great in the future if we worked out how to communicate these crosstalks a bit better. Because preparing this talk, I was like, oh, I have actually no idea what I'm preparing for. And so like I wrote a colloquium talk, and of course in some places it's okay, in other places it's rubbish. So yeah, it would be great if we can iron out the kinks in this program. And have some of you guys on the formal side come and do something else, because currently we have nobody scheduled.
So that was the plan. There was some scheduling conflicts and it comes to push it to next semester.
So spring.
There was a plan and then there was also a faculty meeting, the one last seminar we had, so.
I see.
But next semester, yeah.
Thank you very much.